Okay, today we are doing binomial theorem. We're going to use the binomial theorem to expand polynomials. Basically, when you have a problem like this, x plus y squared, you know how to do that. You just make two of them and multiply it out, right? But what if it was to the fifth? Okay, then you'd have to have 5 of them, and they'd all have to be multiplied. Everything has to get multiplied by everything. Get how confusing that could be to try to put all together? So this is something that comes up in calculus a lot, and so we need the binomial to expand things. When you get into the high-level stuff, AP Calc, you'll need this, or in HL, you'll need this. So there's basically a formula that does this, and I'm going to kind of walk you through the important parts of that. Okay, so I'm going to skip a bunch of stuff, 1, 2, skip a few, and go to this one. We go to this little puzzle. So imagine that those are lava pits. They've built this thing over the top of molten lava, kind of like in the Lord of the Rings movies where you got the building that's got lava inside it. Anyway, so imagine you had to just get from point A to point B. And you don't want to walk in the red lava there, but you could walk this way, for instance, and that's one path to get there. There'd be a lot of paths, wouldn't there? Other than paths that like make you go backwards, which are not allowed, or paths that make you go, again, down. If you ever go down, that doesn't make sense. It's not efficient, right? Like, I know you could do that, but there would have been a better way. You never want to go down. You're only going to go up and to the right. Then how many paths would there be to get from point A to point B? You might note that, okay, there's 5 rows, or this way, or 5 columns actually, and there's 4 rows. So you might think, okay, 5 times 4 is 20. That might be a good starting point. How many think it's bigger than 20? All right, take your best guess on how many routes there are. If you never turn back, you're always heading towards your goal. Write down what you think it would be. I'm just going to get a quick scan of the room. After you write your number down, turn it my way. It's okay if you're not right. Nobody was right last hour. I don't expect you to be right, but I want you to take your best guess. Like, is this a massive number? Is it a kind of contained, fairly small number? I'm going to pause for a second while you turn those my way. Answers. Bottom line is that you guys are all over the place in your guesses. You're not sure at all. And I'd say the average in this class was probably about an 80. It is interesting. It's all in how you say things. Last hour I asked the same question, but I asked it in a different way, and the average was about a 30. And so it's interesting that however I said it to you made you guys realize there must be a fair number of ways to get there, because 80 is closer, but it's higher than that. So how would you actually get this without actually drawing them all? That would be ridiculous. Well, you have to use some logic. Logically, to get from here to here, you're going to have to either go through this intersection or that intersection. Would you agree with that? How many ways are there to get to this first intersection here on the lower right? How many ways are there to get there? Just one. There's only one way. You just walk down the hall and it's there. Okay, so how about this intersection right here? Also one. That makes sense to you? Okay, then how many ways are there to get to that intersection then? 2. Notice it's because you could go through this way or through that way, and so there's 2. All right, to get this intersection, wouldn't I need to say, well, then you're either going to go through this one or you're going to go through this one, right? So what's that lower blue circle? How many ways to get right here? One way. Because you can't go, up and then back down again. That'd be wasting time. We can't waste time. We only can go efficiently from A towards B. So there's only one way to get there. So then how many goes in here? If if there's 2 ways to get here and 1 way to get here, how many ways to get there? 3. Finish the pattern. You'll start noticing some patterns too. I hope you notice that these are 1s all the way across the bottom, for example. Only 1 way to get to that corner right there without breaking the rules, because you can't ever go down and you can't ever go to the left. There's only 1 way to get to that spot, and it's kind of cheating, but we're going to put a 1 right there. In a way, how do you say, how many ways can you get where you are right now? Because that's where you start. All right, I'm going to pause for a second while I'll let you think about this. And by the way, once you get the pattern done, you'll know the answer. You'll know how many ways there are to get from A to B. Because eventually, you'll be getting right there. Okay, did you catch on to some patterns that were in here? Not everything's a pattern, I know that, but there were some patterns. You notice that this row right here is 1, 2, 3, and then 4, and then 5, and then 6. That makes sense? And then going this way, it was 1, 2, 3, 4, 5. This was 1, 1, 1, 1. So there's some patterns that kind of help you out, but then you just kind of got to start doing some grunt work and adding some numbers together. 3 plus 3 is 6. 6 and 4 makes 10. 10 and 5 makes 15. And then 6 and 4 makes 10 here. 10 and 10 makes 20 there. To get to this part of the hallway, there's 20 plus 15 is 35 different ways to get there. And then 10 and 5 makes 15. And 15 and 20 makes 35. And this is 21. And, well, 35 and 21, 30, 40, 56. And then lastly, 70. And so then the piece de resistance, 70 and 56 makes 126. And there was a person who guessed 120, which is a very good guess. 126 was the right answer. Okay. So, my question is, do you see a famous triangle in this data? It's called Pascal's triangle. I'm sure at some point, some elementary teacher or somebody must have showed you this little triangle. I'll start drawing it out and you see if you start noticing where it is. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Do you get how I'm getting these numbers? The 1 and the 1 make 2. The 1 and the 2 make a 3. 2 and the 1 make a 3. Did you see that pattern? Now, I know you may not have ever seen this pattern or this triangle before, but I'd like you to copy down the part I've got right here. You see it right here? Why is it appearing? What do they have in common? The Pascal's triangle and this little problem that we did. What do they have in common? Say it louder. Yeah, they're adding previous numbers. Numbers that are right next to each other get added. All right, so if you're going to take Pascal's triangle 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, would you please make the next row of Pascal's triangle? did you have 1, of course. And 1 plus the 3 makes 4, and 3 plus 3 makes 6, and 3 plus 1 makes 4, and then 1 on the outside. Raise your hand if you had that one right. Okay, good. Math's about recognizing patterns. That's a big part of it. And today's got a ton of patterns. Okay, so then why did I go over that? Because to be able to answer this kind of question, let's make this, I'll just keep it an X and a Y to begin with, as easy as I can. If you had X plus Y to the, let's say, third power, the way you get the answers is you take a row of Pascal's triangle, and those make the coefficients. Do you see where the 3 is in Pascal's triangle? 1, 3, 3, 1. 1, 3, 3, 1. There's 4 terms, and the lead coefficients on them are 1, 3, 3, and 1. Next, would you agree by the time you get done multiplying this thing out, there'd be an x to the third in it? Because you'd have an x gets multiplied by another x, which eventually you're going to get multiplied together enough times you have an x to the third. And there's also a y to the third in it. Okay. So here's how it goes. See if you can catch on to the pattern. X to the third, x to the second, x to the first, x to the 0, which is the same thing as just 1, right? And going the other way, who can do this now? What do you think is going to happen right here? Y to the 0, very good. Keep going. Y to the first, keep going. Y to the second, and Y to the third. There's your answer. We have expanded that binomial. See, it's a binomial because it's got 2 parts. 2 parts is binomial theorem. So I could clean this up a little bit. Do you get that I don't really need to write the 1? And do you get I really don't need to write the y to the 0? So what's the first term really? Next to the third. Plus, this one is the way it is. 3x squared y. And you could put to the 1 if you want, but you don't have to. Plus 3xy squared. And then again, we got some extraneous stuff that we don't really need. The 1 and the x to the 0. So we're just going to write y to the third. There we go. I have expanded x plus y to the third. All right. Let's see if you can figure out this then. 2x plus y squared. Use the pattern. Don't FOIL it out. I know you could FOIL it out. Use the pattern I just showed you. Now, on the test, I would expect to see a lot of people making a little Pascal's triangle off to the side. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. And we don't need to go any farther than that, do we? So which row has the 2 in it? That one. So maybe you should start with those. I'm going to pause for a second and see if you can figure this out. I want to give you a hint. You know how it was x, the x kept getting smaller and smaller? It was like x to the third, x to the second, x to the first, and x to the 0. This time it's going to be 2x to the second, 2x to the first, 2x to the 0. I'm going to pause. I know I could do this one for you, but I think some of you need to struggle with this a little bit. Here's the coefficients you start with. See if you can get me my answers. I'm going to pause while you try that. Okay. Man, you guys are being really quiet today. So, do you get it was 1 2, 1 as the lead coefficients. Raise your hand if you had that part right. Okay, good. Then do you get it goes, one of them goes down while the other one goes up. So I have 2x, notice me putting in parentheses to the second, 2x in parentheses to the first, and 2x in parentheses to the 0. How many of you had that? All right, that was the tricky part. How many of you had this? I bet a lot of you had this part right. Y to the 0, y to the 1, and y to the second. Raise your hand if you had the y's right. Okay, good. Do you get what I just did now? Now that I did it, do you get what I did? Because this term you can't just get in your head that that's just like an x. It can be anything. It could be 2x to the 5th there. All right, so let's actually multiply this all out. Everybody, now that you know what the terms are, would you please multiply them all together? This is all a multiply. There's no distributing happening. It's just multiply this all out, multiply this all out, and multiply that all out, and tell me what the final answer is. And then I'd like you to compare it with the kid sitting across from you. Rows 5 and 6, rows 3 and 4, rows 1 and 2. See if you get the same thing for your answer here. Okay, so this part, y to the 0 is kind of irrelevant. It's just 1. And then 1 times anything is just 1 times, 1 times anything is that thing. So 1 times the 2x squared. Does the 2 get squared? It's in the parentheses. It gets squared. 2 squared is 4x. That first term is 4x. Somebody last hour, I was proud, they said, you know what, this is pretty much exactly the same thing as that top 20 kind of problem. Yes, it is. And that's why, see, there's this many people looking around with confused faces, and this is a complicated thing enough if you understand exponents. That's why we do exponents in the top 20. All right, so back to this. 2 times 2 to the first would be 2 times 2, which is 4. 4x, y for that term. And then the last term is anything to the 0 power is 1. That's gone. 1 times 1 is 1, and 1 times y squared is just y squared. There's your 3 terms. I put pluses in between them. Why am I not putting any minuses in? Because there's only pluses in the problem. That makes it the simplest kind, of course. So there's the answer except for that squared. Okay. How many of you had that one right? Ooh, that's more than people than you just weren't confident, apparently. Okay, let's do one more like that. Let's say it's m minus p. Notice that's a negative p. And the negative p is going to be cubed and then squared and then etc. So this is to the 3rd. Everybody give that one a shot. Just a hint here. I'd probably start by making that Pascal's triangle. Anytime you have a problem like this. I'll have to go further than that, but that's a start anyway. Okay, let's see who the die of destiny wants me to call upon right now. There we go. I got a couple. Okay, row 6, last person. That's you. Tell me what the next row is in Pascal's. 1, 3, 3, 1. Good. So then, therefore, the coefficients are 1, 3, 3, 1. And then tell me, what's the trick for doing this one? M cubed, and then, yep, and then, yep, and then m to the 0, which we could just like get rid of right away because we're not going to have any. M to the 0 just means 1, right? Okay, so then the rest of them. Ooh, notice I'm using negative p. Very good. To the, what? To the 0. And by the way, what is negative p to the 0? 1. Anything to the 0 is 1. Okay, and then keep going. Which would be what? negative p. Okay, keep going. And, all right, now if you can actually grind out the little algebra, not really algebra, well, it's mostly exponent stuff. In each of those four terms, you'll be able to write the final answer. Who's confident that they have it this time? Come on, be confident. All right, there's like 8 people that are confident. All right, Die of Destiny. Who should they call on? That's weird, it was the same person again. Not doing that. Overruling Die of Destiny. That would be you. M to the third. Minus, why a minus? P is negative, and when you put it to the first power, it's still negative. Okay, keep going. What if somebody put p m squared? Is that okay? Yes, it is. Okay, keep going. Plus, isn't there a minus in that one too? But it's squared, so that gets rid of the minus, and then it becomes... Okay, keep going. Perfect. Raise your hand if you had that one right. Good. So that's the basics of binomial expansion. Okay, of course, it can get a little more complicated. I'm just going to give you one more that steps it up just a little notch. Use binomial to do this. I know you could FOIL it, but I'm trying to avoid having to make it really big and long. So just use binomial. All I need is the 1, 2, 1, right? Mr. V, help me get started. Did you put it in parentheses like this? Oh, awesome. Yep. Ooh, interesting. It's 3x to the 0, so no 3. I could see what you were thinking, though. But the whole thing is to the 0, so the whole thing becomes 1. So that part's going to disappear. Okay, and then the other one? Oh, sorry. You're right. Thank you, sir. Nice. Finish it off, Miss J. 3x squared. Good. Not negative because this part turned into 1. Okay, keep going. All right, there's a 2 at the front, and there's a 3, and there's a negative 2 here. Put them all together. Three times 2 is 6. Keep going. All right. And keep going. X and Y. You are correct. I was a little nervous on that one. Did I do that one right? Okay, good. And the last one. This part right here. For Y. I think the right word for that is 2. Sounds like cube, but it's squared. Okay. All right, good. There you go. Raise your hand if you had that one right. Oh, did I do something wrong? Oh, the 3 get, oh, yes, that should be 9. My bad, I didn't catch that. This 3 has to get squared, so it is a 9. There's so many opportunities to make little mistakes. Like you have to, it's like a minefield. You have to not make mistakes like 12 times to get this right. So many little tiny parts. Okay, so that's binomial expansion. Now, where we're going to go with it is to learn this formula, because this is 3 terms that have been generated by this process that we were doing. That's a sequence. That's why we followed up our sequence little part with this, because there's a way to write this as a summation. But it's kind of like the quadratic formula. It's this big formula that will generate these. It's a little term generator for binomials. It's called the Binomial Theorem. I'm not going to actually launch that till tomorrow, because you can already do these without the Binomial Theorem. You're already getting the answers. This was the answer. It's just the Binomial Theorem can do it, and it can do it in a series. So you got to be able to put the 2 together. Like you did series like this, where I'd say this is 2n and n equals 1 to, let's say, 4. And this is a generator that will tell us all the terms and what coefficients have to go on each term. And it's kind of cool. Yes? I gotcha. But you're dependent on Pascal's triangle to do it. There you go. If you're going to do it to the 52nd power, you're going to be a little tired drawing that Pascal's triangle. Yes. So this term generator will work just fine for the big ones. What I just showed you kind of shows you the basics of making them. And as long as you keep the powers down, it works fine. All right, so I just want you to remember sequences for just a moment. That is supposed to be the sum of a whole bunch of terms. Would you just write down for me the first 4 terms of that? First term comes out to this, second term comes out to that. It's not too tough. So the first term, you just stick them 1 in, and you get 2 times 1 is 2. Stick in a 2, you get 4. Stick in a 3, you get 6. Stick in a 4, you get 8. Raise your hand if you had that right. Okay, good. So the binomial theorem has something like that, but it also has, just a second, it also has these in it. To generate the coefficients, you use these. Do you remember these from probability? It's kind of the unit we were using them in. It's like if you have 3 things, like you won't be able to see this at home, people in the video, but I got 3 things on my desk. I got this remote, I've got this infinite staircase, and I've got this marker. Okay, if I have 3 things and I want to take combinations of 2, how many combos of 2 are there? Well, you can take these 2, or these 2, or these 2. Okay, so there's 3 combos of 2. Does the order matter? No. If it order mattered, it would be a P problem. These are not P's. These are going to be C's. Okay. So there's a formula for generating that. Does anybody remember the formula? It involves factorials for generating that. Figured you might not. So, ready? Everybody write this down. You're going to want to remember this. Okay, so it's 3 factorial over, does that ring a bell? What do you do with the other? What do you do with the numbers now? Can you do this? There is a 2 factorial in it. Yes, because it's what? How'd you get the 1 though? 3 factorial minus 1 factorial. Or sorry, 3 minus 2 factorial. Notice what I'm doing here is I take this number and you put it on the top. I take this number, I put it on the bottom. And then I take this number minus this number and I put it on the bottom also. All right, if you understood that and you understand what factorials are, I'm just going to remind you what they are. Say I had 5, 4, 3, 2, 1 over 3, 2, 1, Do you get how the 3, 2, 1 would cancel? And then I just have 5 times 4, and so the answer is 20? Okay. So would you please try this one? What is 4C3? If you're stuck, or if you're not, compare with the person sitting next to you. See if you get the same thing. If you're not remembering what the factorials were, ask them. Okay. In case you haven't caught on the pattern yet, it's 4 factorial over 3 factorial with an extra 4 minus 3 factorial. Does that ring a bell? Okay, so then it's 4 factorial, 4, 3, 2, 1, over 3, 2, 1, and 4 minus 3 is just 1 factorial, which is just 1. Okay, so that cancels that, and the answer is 4. Raise your hand if you had that one right. How many of you had it right? Raise your hand one more time. Okay. All right. We're going to do one more like that, because if you get it, it's going to go quick. 5C2. Okay, so at least you're taking notes then, right? Okay, good. Doesn't look like you've taken any notes since we started factorial. I'd recommend taking some notes. All right, so 5 factorial on top over 5, sorry, the 2 factorial, and then a 5 minus 2 factorial. See, like something like that would be a good thing to have, because this would be something that's on your final and on the last test, so it counts double, because this will be on your next test. All right, and this, I'm just doing this warm-up for you, because in the binomial, they use this to generate the lead coefficients instead of Pascal's triangle. So when the numbers are really big, you have to use that. Calculators will be allowed on this test. All right, so then 5 factorial, 5, 4, 3, 2, 1. 2 factorial, 2, 1. And 5 minus 2 is 3 factorial, 3, 2, 1. So I'm going to cancel those. And then I got 5 times 4 over 2. 5 times 4 is 20 over 2 is 10. Raise your hand if you had 10 for an answer. Okay, good. That's the part that's going to generate the lead coefficients. All right, so it'll be like, okay, so I did all that, and I now know that 10 is the lead coefficient, instead of having to do it with Pascal's triangle. Okay. Last thought. What do you think that means? I don't know if you've ever seen that before. It's not a matrix. Otherwise, it'd be more rectangular. Come on, you can make the leap. It's related to what we were just doing. What do you think? Close. What do you think? 9's like the 5, and 4's like the 2. So what does this really mean? 9C4, which would mean 9 factorial over 4 factorial, yes, to start with, but then the one last piece, which is 9 minus 4, which is 5 factorial on the bottom. Okay, there. Now you're all set up so that when I show you this in a formula, you won't freak out because it's just combinations. All right, so let's get to, actually, I really like this problem. Do you see the setup here? Does it look kind of triangular? Why am I going to put a 1 there? You got it. Why do you think I'm going to put a 1 and a 1 here, besides the fact that that's Pascal's triangle? They're the coefficients for this problem, right? What is the answer to that problem? A plus B, couldn't I say 1A plus 1B? See where I'm going with this? Okay, what's the next thing in Pascal's triangle? Oops, sorry. A little premature for the 3. 1, 2, 1. Okay, and then remember how to do this? Fill out the rest of the pattern. Remember, it gets, the A starts big and gets small, and the B starts small and gets big. So A starting big would be A what? A squared, and then keep going. A, and then A to the 0, which is just 1. And then what? B to the 0, B to the 1, B to the second. So there's your answer. Do the last row. Compare it with the kid sitting next to you. It's the last problem, by the way. Try this last problem. Sums up everything that you've learned. Mr. PA in the back row, what's the coefficients? 1, 3, 3, 1. Excellent. Let's pick a random person to do the A's for me. Row 6, person 2. Yep. A cubed and then A squared. Yeah, so I'm just going to leave it off because A to the 0 is really not going to be needed. And then random person, and it's last person in this row.
So B to the 0 is 1.
Final answers. Would you sum it up for me? Clean it up.
1, or A to the 3rd.
A to the 3rd.
Plus A squared plus 3rd.
Don't forget the coefficient. There we go. Okay. You now can do a binomial expansion. Now I want to show you what, okay, here's the scary looking formula that tells you how to do the P's and C's. Actually, it doesn't do P's, it just do C's. And it says the binomial coefficients. See, that's why we're going to do that. This is that n factorial over a j factorial and an extra n minus j factorial. Okay. Anyway, the assignment for today, it's on like page 37. Way down here. There we go. I'm going to have you skip number, let's see, number 9. And a lot of these are super easy. But when you get to something like this, don't like go, I've never seen that before. I can't do that. It's really not hard. There's a number, n, and then there's a number, n plus 1, which is obviously 1 bigger. You understand how to handle, like, if it was 6 factorial over 5 factorial. It's not super hard. I might have to think about it for a couple minutes, but it's not super hard. Okay, 10 and 11 are just plain old, use Pascal's triangle to expand it. That's the That's the way we've taught you so far. You don't know the binomial theorem yet, but you're getting close. And then these two, I'm going to have you skip number 13 just because I want to cut the assignment down because I'm not giving you much time to work. So skip number 13. And then this one is, do you get that that's just an expansion problem and they just want to know somewhere in the answer there's an x to the third and which part, you know, like if you're all done and you got like a whole bunch of parts to your answer, right? And one of them has an x to the third in it is all they're saying. They want to know what's the rest of that term. Okay, so it's not super hard, but this is a kind of a tough one to expand. So that's what makes it a hard problem, is just expand this. Notice it's got the 2x, so it's going to have, okay, have to make Pascal's triangle, so I got to go 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. Help me keep going here. What's the next one? 1, 4, 6, 4, 1. And is that the right one? Nope. Got to go one more. What is it? 1, 5, 10, 5, 1. Right? 2 tens? You're right. 2 tens. There we go. So then the lead coefficients are 1, 5, 10, 10, 5, and 1. And then I start here with the 2x, and I do my 2x thing. And it's either, am I going to go, usually the first one you do, you start big and you get smaller, right? So 2x to the what? And don't make the mistake that I made on that last problem where I just said, oh, so that's 2x to the fifth, right? It's 2 to the fifth and x to the fifth, so it's what? 2 to the fifth is 32. Good. 32x to the fifth. All right. Is that the term I wanted? Reminds me of the book, Are You My Mother? I love that book. This bird keeps going around looking, trying to find its mother. It's very cute. Anyway, so then this next one would be a 2x to the fourth and a 2x to the third, etc. I think you can handle that. And then the other ones are the negative y's. Notice the negative y. So it's going to be negative y to the, what do I start with on this? 0. And remember, anything to the 0 equals 1. So what's negative y to the 0? It's 1. Don't think that that adds a negative. It does not. And then you simplify, clean up this term right here, and that's your first term. Will that have an x to the third in it? Nope. It has an x to the fifth in it. One of them does, though. Ooh, I think it's this one. That makes sense to you? Because it's got a 2x to the third, so which is going to make a 2 to the third is an 8. And the 8 times the 10 makes 80. So it's 80x to the third. And then I just got to figure out my y term, and I've got it. This is the one that has an x to the third in it. That's all they're saying. Now, there is a fancy way that I'll show you tomorrow that you can find this without having to actually multiply all of the other ones out. You can logically figure out which term's going to have it in it. The third term's going to have it in it. But I can show you that later. For right now, you can answer this question. I've already done a bunch of it. So, and that's all there is for day one. So, that's your homework for tonight. It is a very reasonable assignment. Some of you have not been doing your work, and it's going to come back to haunt you in bad grades on this next test and on the final. So get back on the horse. You've got time here to get yourself straightened out, and this is an easy one. Get a good one in the books. Okay? All right. There'll be a couple on here that stretch you just a little bit, and if that's too much for you, don't sign up for Honors Pre-Calc second semester, because there's nothing really challenging here. And it actually, you should be like, yeah, this is easy. And granted, there's a few parts that are a little detail intensive, but it's not like we're asking you to do super complicated stuff here. So get this one done. That's all I have for you for today.